All right, welcome back to another extremely exciting video on geometry coming from Mr. Hawkins' dining room. Today we're going to finish up or talk about two-dimensional measurement called area. And I have one more thing to teach you in that, and I'm going to review everything we've done so far like I do every time. Then I'll show you the new stuff and you'll have homework on that. But first, the objective for the day is to be able to calculate geometric probability. This is an important concept because it kind of shows up on the SAT pretty frequently, so you can kind of get this down. All right, so in any event, first thing we started off with this unit was parallelograms. Again, that's just going to be base times height, where base and height have to be perpendicular. Here's the perpendicular, so this one would be 12 times 4 because they are perpendicular. That's the base and the height, so that's 48. Triangle, remember, was just a half of parallelogram, so it would be 1/2 the base times the height. Still have to be perpendicular. Here's the perpendicular. That means this is the height. Now the base would just be this portion, which has to be a side of the triangle. So this would be 1/2 6 times 10, which is 30. Trapezoids, remember they had that long formula. That's what 1/2 the height times base 1 plus base 2. Height has to be perpendicular. Here's the perpendicular. That means 8 is the height. And then the two bases are 8 and 16. So that's going to be 24 times 4, 96. Kites and rhombi, remember they had the same formula. It was 1/2 d1 times d2. D stands for, these D's stand for diagonals. In a rhombus, remember that diagonals are going to bisect each other. So if this half of the diagonal is 12, so is this half. If this half of the diagonal is 8, so is this half. So that means 1/2 the one diagonal would be 24, or 12 plus 12. The other diagonal would be 8 plus 8, which is 16. So that would end up being 12 times 16, which is 192. Then we talked about circles and sectors. Remember, circles had an area of pi r squared, where r is the radius. The sector was just a slice of pizza, like you have in this example right here. You take that central angle, put it over 360, and then multiply it by pi r squared. That's what we're going to do on this one. Central angle is 110 over 360, and then I need to multiply that times pi times 6 squared. So on this one, I would do 110 divided by 360, figure out what that is, and then just multiply that times pi 6 squared. Just like that. So it's 34.6. Regular polygons, they use the same formula for all of them, and that was 1/2 a times p. A is the apothem, which goes from the center and is perpendicular to a side, so that's my apothem. P is the perimeter. So in this shape, it'd be 1/2 of the apothem 6 times the perimeter, which would be one side is 8.2, and then I have 1, 2, 3, 4, 5, 6 sides of 8.2. So I'd multiply that times 6 to get the perimeter. Plug that all in my calculator. I would do 8.2 times 6, that's my perimeter, times 6 times 0.5, and I end up with 147.6. So 147.6. Then we looked at composite figures. Remember, you add up all the pieces. So again, I break this into pieces, probably something like this. So then I have a 3x6 rectangle, which means that's 18 square units. Down here, if this is 5 here, this is 3 here, this is 2. All right, so if this whole unit here is 3, this part of it is 2, that means the remaining piece has to be 1 here. And then I could say that this is 2 by 5, which is 10. And then how long is that? So let's say this dimension here is 1, since 6 is 1 more than that, so that would be 1. So then I just add up all those areas. 18 plus 1 plus 10. So that's 19, so that's 29. So just add up all the pieces. Similar polygons, remember, it uses ratios. You have a side ratio and an area ratio. Side ratio, if it's a to b, that means the area ratio is going to be a squared to b squared. Just square it. So here I can get the side ratio because I have a pair of corresponding sides. So the side ratio is going to be 8 to 12, which goes down to 2 to 3, which means my area ratio is going to be 2 squared over 3 squared. So that I'm going to use in a proportion to find that missing ratio. So that would be what? 4 to 9 is equal to 14 to x. And then you cross multiply and solve, and you end up with 4x is equal to 9 times 14, which is 126, and I divide that by 4. And I end up with 31.5. So that's everything we've done in the area so far. So the new information talks about geometric probability. So a little review of probability. We've done that in the past. You even did it last year in algebra. But probability is the likelihood of something happening. Likelihood of something happening. It has a formula, and so the probability of some event is kind of the way it's written. Probability of some event is equal to a fraction. In the numerator of the fraction, that's the number of successes. Whatever the event is, this is the number of ways that this event can happen. In the denominator is the total number of things that can happen. So simple examples. So we use it with rolling a die. So if you have a 6-sided die with 1 through 6 on it, the probability of rolling that 3, again, there's only 1 3 on the die, so the number of successes would be 1. Everything that could happen, well, there's 6 sides on that cube, so it's going to be equal 1 over 6. Rolling an even number, so now on a die, remember if a die is 1, 2, 3, 4, 5, 6, this is even, this is even, this is even, so that's 3 successes out of a total of 6. I can reduce that down to 1 over 2. Probability can be either written as a reduced fraction like I did here, or it could be written as a decimal, or you can move the decimal place over 2 times and you could write it as a percent. Multiple of 3, let's see, 3 is a multiple of 3 because 3 times 1, and then 6 is 3 times 2. So there are 2 successful multiples of 3 out of 6 things that can happen, which is 1 over 3, which is 0.33, repeating, which is equal to 33.3%. So that's a review of probability. All right, we're going to apply it to geometry. You're going to see it in 2 ways with geometry. You can do it with length. So geometric probability, here you should say applying laws of probability. To geometric figures. So the first kind you're going to see is length. And basically what you have is you're going to have a line segment. And you can have a point fall anywhere between J and M. It can't fall anywhere but on this line somewhere. So again, you're going to find a point on this line. So now the probability that the point is going to, point X is what they're calling the point that I'm talking about, that's going to fall on KL. Well, a successful place to fall would be this distance here, which is 7. So since that's a success, that goes up top. Everything that could happen, if it can fall anywhere between J and M, you'd add these up. So this is 10 plus 4 is 14. So again, that would be a 1 out of 2 chance, 0.5 or 50%. If fall on LM, well, LM is 4, which would be a success. The whole thing is still 14. That goes down to 2 over 7. So if you wanted to write that as a decimal, you just go 2 divided by 7 on your calculator, and that's 0.29, we'll call it, which is about 29%. And then if you want to fall on KM, KM then is 11, so that's a success. Out of 14, 11 out of 14 is 0.79, which is about 79%. And lastly, what's the probability of landing on JM? Well, it has to fall on JM somewhere, so the whole thing is a success. Everything that could happen is also 14. So that has a probability of 1 or 100%. So that's using length. Another way you can view probability geometrically is using area. So there's two types of area problems. This is the first type here, and this is the second type here. We'll look at the second type first here. So in the second type, notice there's no numbers. All I have are equal pieces. So these are all equal squares, basically. So when that happens, all you have to do is just count up the number of successful. So you're going to be, the probability of falling on the shaded region is what we're looking for. Probability falling in shaded region. So you can kind of view it as a dartboard. If you're throwing darts at a dartboard here, the dart has to fall on the board. That's the only rule. It can't like hit the wall or fall off and fall on the ground. It has to land on the dartboard somewhere. So once you know the probability of landing in these shaded areas, again, if I'm randomly throwing it at the dartboard, a success would be landing on one of these shaded regions, of which there are 1, 2, 3, 4. So a success would be one of those 4 regions. Now, how many total regions are there? Well, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 total. So 4 out of 9, again, as a decimal, that would be 4 divided by 9, which is 0.44, or 44.4%. Up here, so that's one kind. I call this equal spaces. And there's no real number measurements on here. Over here on this example, it wants me to find the probability. Again, it's a dartboard. What's the probability of me randomly throwing the dart at the dartboard and landing in that circle region? So again, outside here, if the dart lands out here, that is not a success. I want the probability of it landing in the circle region. So a success would be that area of that circle region, which is a circle, which would be pi r squared. So this would be pi 3 squared, which is equal to 9 pi. So success would be 9 pi. I'll use the calculator on that eventually. Now, everything that could happen? Well, everything that could happen is falling in this whole rectangle here. The area of that is going to be base times height, because it's a rectangle. So that would be 7 times 6, or 42. So that's everything that could happen. So you can leave it just like that, or you can plug it in your calculator. Again, I figure out what 9 pi is by doing that. And then I take that and I divide it by 42. So I end up with 0.673, or 67.3%. So down here is another one like that. Here I want to find the probability of landing in a shaded region. So again, this is the dartboard. This is not a success because it's not in the shaded region if the dart landed there. But again, I want to find the probability of it falling in one of those shaded regions, which means I have to put the shaded area over everything. So area of everything would go on the bottom. That's easy to figure out because it's that rectangle again. So this is where the dart has to fall. That would be area is equal to base times height because it is a rectangle. So this would be 10 times 11. Which is 110. So that was the easy part. Hard part of these shaded areas, I have to get the area of a triangle. The area of a triangle, remember, is 1/2 the base times the height. So half of the base would be 6. And then the height's perpendicular to that at 3. So that's equal to 9. Then this is also a shaded area. That's base times height because it's a rectangle. That's just 2 times 6, which is 12. So now this and this is a success. So I do 9 plus 12 in the denominator, or in the numerator. So then on my calculator, I would just do 9 plus 12, and then divide that by 110. And so that would be 0.19, or 19%. Then the last kind is a spinner problem. Again, a whole circle is 360 degrees. So again, if I want to find the probability of it landing in 3, that's this section here. Success would be 122 degrees out of a total of 360 degrees. Probability of landing in 1, success is 26 degrees out of 360. 1 or 5 would be those two added up over 360. So that there's bunch of different types of geometric probability problems. See what you can do. Use this video. I'll also put the answers to the homework up.